Hello and welcome to this week's lesson. We're going to start talking about the Laplace transform. We will cover sections 4.1 and 4.2. Before we begin, I want to do a quick bit of revision from first year calculus. Let me remind you that if we see an integral from some number a to infinity, what this really means is the limit as capital R tends to infinity of the integral from a to r. So, for example, assuming that c is non-zero, we can calculate the integral from 0 to infinity of e to the power ct. And this really means the limit as r tends to infinity of the integral from 0 to capital R of this function. Or the limit as r tends to infinity of 1 over c e to the power ct between 0 and r, which we can calculate is equal to infinity if c is a positive number, or minus 1 over c if c is a negative number. One more example. Let's suppose I wanted to calculate the integral from 1 to infinity of 1 over t. This really means the limit as r tends to infinity of the integral from 1 to r of this function, which we can calculate is equal to infinity. Another idea which you may or may not have seen before is the idea of a piecewise continuous function. This function which I've drawn at the top of the slide is not a continuous function, of course, because it has these free jump discontinuities. But it's made up of 4 continuous pieces. A function like this we say is piecewise continuous. Each one of these pieces is a continuous function. Let's be more precise. Let's suppose there exists a finite partition, and let's suppose on each one of these small pieces the function is continuous, and let's suppose that at every one of these endpoints both of the one-sided limits exist and are finite. Now I'm ready to introduce the Laplace transform. The Laplace transform is named after a French mathematician, Simon Laplace. What is the Laplace transform? We know what the derivative is. The derivative takes a function and it changes it into a new function. If we start with a function f of t and we apply the derivative changes our function into a new function which we call f prime. The Laplace transform is another way to change a function. If we start with the function f of t, the Laplace transform changes this into a new function which we're going to call capital F. And we're also going to change the variable. Instead of being a function of t, we're going to call capital F a function of s. Let's look at the definition. First of all, I'm just being careful. K, M, and A are numbers. F is our piecewise continuous function. And the third condition says F doesn't get too big too quickly. We'll skip past these because for this course, these 3 conditions are not particularly important. But what is important is the formula for the Laplace transform. The Laplace transform of small f is a new function called capital F, which is defined to be the integral from 0 to infinity of e to the power minus st f of t dt. When we write integral from 0 to infinity, really we mean the limit as capital R tends to infinity, etc., etc. So we have our original function, small f, we calculate this integral, and we have our new function, which we can write as capital F of s, or we can write this as curly L of small f of s. This curly L symbol, you can write it whichever way you want. Usually, if we have a pen, we write it like this. A couple of curl at the top, curl at the corner, and a bend at the end. You can use any type of fancy L you want to draw, as long as it doesn't look like your ordinary L. Here's my ordinary L. Make sure these two symbols look different. And we could say that the new function, capital F of s, exists for s greater than a. I'm going to go through some examples. I put the formula at the top so that we can, because we're going to use this formula. Easiest function I can think of is the function 1. The Laplace transform of the function 1, instead of f of t, we write 1 just here. So we're calculating integral from 0 to infinity of e to the minus st multiplied by 1 dt. Of course, that means the limit, and the integral of the integrand is, or an antiderivative of the integrand is minus e to the minus st divided by s. When we calculate this, we get 1 divided by s, and this exists if s is greater than 0. Another one. The Laplace transform of e to the power at for some number a. Here is our function f of t. We'll put this into the formula, and we're calculating the integral from 0 to infinity, e to the minus st, e to the power at dt. Here's the calculation. We can calculate this integral is 1 divided by s minus, so 1 over s minus a, which I shall leave for you to calculate. So this means that the Laplace transform of the function we started with, e to the power at, which we might say is a function with domain from 0 to infinity, is this new function 1 divided by s minus a, which is defined between a and infinity. One more example. Let ft be equal to 1 between 0 and 1, be equal to some number k, doesn't matter what the number k is, if t is equal to 1, and the function is equal to 0 if t is strictly greater than 1. I want to calculate the Laplace transform of this function. I want to calculate f of s, or to say this another way, the Laplace transform of small f of s. I want to calculate the integral from 0 to infinity of e to the minus st ft dt. Now, we don't care about what happens at t is equal to 1. We're interested in the first part and the second part. The first part, the function is equal to 1. The second part, the function is equal to 0. So between 0 and 1, we're going to have an integral with a 1 just here. Between 1 and infinity, we're going to have an integral of 0. But the integral of 0, of course, is just 0. So really, we're just calculating the integral from 0 to 1 of e to the power minus st. And we can calculate this. We know how to do this. We get 1 minus e to the power minus s divided by s. And this is defined as long as S is strictly greater than 1. Next function. Find the Laplace transform of sine 80 for some number A. We're going to need to use integration by parts. First of all, let's start with our formula. Capital G of S, or the Laplace transform of small g, is the integral from 0 to infinity e to the minus st sine 80 dt. And of course, if we have a limit from 0 to infinity, an integral from 0 to infinity, really it means limit of an integral from 0 to r. I want to calculate the integral of e to the minus st multiplied by sine 80. And I'm going to use integration by parts. The integration by parts formula is the integral of uv prime is uv minus the integral of u prime v. So I'm going to differentiate the green function, differentiate e to the minus st, and I'm going to integrate the orange function, integrate sine 80. And then take the limit, I get 1 over a minus s over a integral from 0 to infinity e to the minus st cos 80. At the top. Then we have an integral of two functions multiplied together, e to the power minus st and cos 80. So we can use integration by parts a second time. And this time I'm not showing the details. I'm leaving this for you to fill in the gap. If we use integration by parts a second time, we get 1 over a minus s squared over a squared, integral from 0 to infinity, e to the minus st sine 80 dt. But this should look familiar. This integral is exactly the integral we started with. This integral is capital G of S. So we have that capital G of S is equal to 1 over a minus s squared over a squared, capital G of S. We can rearrange this equation to find that capital G of S is a divided by s squared plus a squared. We could do the same thing for cos 80. And we would get almost the same formula. In the previous example, we had a divided by s squared plus a squared. For cos, we have an s on the top. I'm going to leave this calculation for you to prove. Exactly the same as the previous one. Use integration by parts 2 times and then rearrange, and you will be able to find this formula. Or we could do this for sine. Let me remind you that if I had sine 80, it was a over s squared plus a squared on the bottom. For sine, we do exactly the same calculation, integration by parts 2 times. We find almost the same thing, except we have a minus sign on the bottom. Or if we'd used cosh, the Laplace transform of cosh 80 is s divided by s squared minus a squared. And these two formulae are true if S is strictly greater than the absolute value of A. The Laplace transform is a linear operator. Precisely, the Laplace transform of C1 F1 plus C2 F2 is equal to C1 Laplace transform of F1 plus C2 Laplace transform of F2. And this just comes because the integral is also linear. I'll leave this theorem for you to prove. Just use the formulae. Just use the definition of Laplace transform. Just use the fact that an integral is linear, and you can prove this. For example, let's suppose we want to find the Laplace transform of this function h of t. I want to find the Laplace transform of 5 e to the minus 2t minus 3 sine 4t. And I'm going to use the fact that the Laplace transform is a linear operator to separate it like this. 5 multiplied by the Laplace transform of e to the minus 2t minus 3 Laplace transform of sine 4t. We know a formula for the Laplace transform of e to the minus 2t and for the Laplace transform of sine 4t. So we know that we have 5 multiplied by 1 over s plus 2 minus 3 multiplied by 4 over s squared plus 60. And we know that this is true if s is strictly greater than 0. We also have an inverse Laplace transform. If we know that capital F is the Laplace transform of small f, then small f is the inverse Laplace transform of capital F. For example, the Laplace transform of 1 is 1 over s, and the inverse Laplace transform of 1 over s is equal to 1. The inverse Laplace transform is also a linear operator, and I'm going to leave this for you to prove. For example, find the inverse Laplace transform of 10 divided by s squared minus 25. Now, we've done something similar to this before. We know that the Laplace transform of sine at is a divided by s squared minus a squared. And we have roughly the same thing here. Instead of a squared, we have 25, so clearly a is 5. But on top, we don't have a, we have 10. We need to rearrange our function slightly so that it looks like a Laplace transform that we already know. And for this simple example, all that means is taking a factor of 2 outside the inverse Laplace transform. We're calculating 2 multiplied by the inverse Laplace transform of 5 divided by s squared minus 25. Because you know how to do this. Because this is then 2 multiplied by sine 5t. Another example, find the inverse Laplace transform of 1 over s plus 1 over s minus 2. Because the inverse Laplace transform is linear, we can split this up into 2 inverse Laplace transforms. We know these already. We've already looked at these ones. The inverse Laplace transform of 1 over s is 1, and the inverse Laplace transform of 1 over s minus 2 is e to the power 2t. Theorem, and here's a formula which we will find useful. The Laplace transform of t to the power n multiplied by some function f of t is equal to minus 1 to the power n multiplied by the nth derivative of capital F, where capital F is the Laplace transform of small f. I want to prove, first of all, I'm going to prove that it's true if n is equal to 1. So I'm going to start with the right side, but putting n equal to 1 in. So minus 1 to the power 1, 1 derivative of capital F. Minus the derivative of the Laplace transform of capital F. Using the formula, that's the integral from 0 to infinity, e to the minus st ft dt. And because all of our functions are nice functions, the exponential function is a nice continuous function. Small f is a piecewise continuous function. Because everything is nice, we can take the derivative inside the integral. I'm being a little bit lazy here. Remember, integral from 0 to infinity really means the limit as capital R tends to infinity of the integral from 0 to capital R. But I don't want to write that every time. When I write integral from 0 to infinity, I'm assuming that you know I really mean a limit. So let's differentiate the integrand. We're differentiating with respect to s. So there's only one s. So we're only differentiating e to the power minus st to get minus t e to the power minus st. Minus signs will cancel. Rearrange slightly. I have integral from 0 to infinity, e to the power minus st, t multiplied by f of t. But of course, this is just the formula for the Laplace transform of t multiplied by f of t. So the theorem is true in the special case that n is equal to 1. By using this formula repeatedly, we can also show this is true for n equal to 2, n equal to 3, n equal to 4, etc. Next, I want to use this to calculate the Laplace transform of t squared to the power multiplied by cosh 2t. I've written the relevant formula at the top. The formula on the left comes from the theorem that we've just proved. The Laplace transform of cosh at is s divided by s squared minus a squared. So first of all, using the left formula with n equal to 2, this is equal to minus 1 to the power 2, and then 2 derivatives of the Laplace transform of cosh 2t. Minus 1 squared, of course, is just plus 1. The Laplace transform of cosh 2t is s divided by s squared minus 2 squared. And you know how to use the quotient rule to calculate a derivative like this. You can check that this is 2s, s squared plus 12 divided by s squared minus 4 to the power 3. Next, find the Laplace transform of t to the power n. I'm going to use the formula again, but this time the function f will be equal to 1. I want to calculate the Laplace transform of t to the power n multiplied by 1. That's minus 1 to the power n, n derivatives of the Laplace transform of 1. The Laplace transform of 1 is equal to 1 over s. So we have minus 1 to the power n, and then n derivatives of 1 over s. And we obtain the formula n factorial divided by s to the power n plus 1. I suggested that you have a table of elementary Laplace transforms with you. I want to look through this page now. Some of these we've done. The Laplace transform of 1 is over s. That was the first one we did. The Laplace transform of e to the 80. The Laplace transform of t to the power n we've just done. Sine, cos, sine, and cosh we've talked about. Sine I proved. The other three I left for you to prove. We scroll down. T to the power n e to the 80. We could use the formula we've just used. T to the power n multiplied by some function. The next four we haven't looked at yet. These will come next week. And let's see. Not next week, next lesson, I mean, in 2 weeks' time. And the formula I've circled we will do in 3 weeks' time. And then the bottom function, t to the power ft, that's the theorem we've just done. Next example. Find the inverse Laplace transform of the natural logarithm of 1 plus 1 over s squared. Again, we're going to use the formula from the previous theorem. The Laplace transform of t to the power n f of t is equal to minus 1 to the power n, nth derivative of capital F. We're going to use this with n equal to 1. And then we're going to take the inverse Laplace transform of both sides to get t multiplied by f of t is minus the inverse Laplace transform of df dt. So this is what we do. We take our function capital F, we're going to differentiate this function and take the inverse Laplace transform of df ds. So derivative of the natural logarithm of 1 plus s squared. Using the chain rule, this is minus 2 over s cubed, 1 over s squared, which we can simplify to minus 2 over s squared plus 1. That means that t multiplied by f of t is the inverse Laplace transform of this function. To go further, we need to write this function in partial fractions. Partial fractions you studied in first year calculus. So hopefully this should be revision for you. Two divided by s squared plus 1. I want to write this into two functions. One function divided by s and one function divided by s squared plus 1. And on top there's going to be something. On top of the s, which is going to have some number a, on top of s squared plus 1. S squared plus 1 is a second degree polynomial, so on the top we must have a first degree polynomial. The top of these functions must always be 1 degree less than the bottom. So because the bottom is a second degree polynomial, on the top we must have some first degree polynomial. We must have bs plus c for some numbers bs and c. We need to calculate a, b, and c. By putting these functions over the same denominator, we get a, s squared plus 1 plus bs squared plus cs, or a plus bs squared plus cs plus a. Now, straight away, a must be 2. There's a cs, and over here on the left, there's a 0s. So c must be 0. On the right-hand side, we have a plus bs squared, and on the left side, we have 0s squared. So a plus b must be 0. We can say that a must be 2, b must be minus 2, and c must be 0. So we get 2 divided by s minus 2s divided by s squared plus 1. Therefore, t multiplied by f of t must be the inverse Laplace transform of 2 divided by s minus 2s over s squared plus 1. At this point, we need our table of elementary Laplace transforms. I'm looking for something in the middle column which looks like a number divided by s. And here it is. I have 1 over s in my middle column. I'm also looking for something that looks like 2s over s squared plus 1. And here it is. The Laplace transform of cos at is s divided by s squared plus a squared. We write these at the bottom. The Laplace transform of 1 is 1 over s. The Laplace transform of cos at is s over s squared plus a squared. Now that we know where we're going, what we want, which functions we want to end up at, we know how to break up our inverse Laplace transform. We know that we should take the number 2 outside, and we're looking at 2 multiplied by the inverse Laplace transform of 1 over s minus 2 multiplied by the inverse Laplace transform of s over s squared plus 1. Which of course is 2 minus 2 cos t. And then we're almost finished. After we divide by t, we know f of t. Therefore, the answer to this example is f of t is equal to 2 multiplied by 1 minus cos t divided by t. So that's what the Laplace transform is, but why are we studying the Laplace transform in our differential equations course? we're studying the Laplace transform because of this very important formula just here. The Laplace transform of the derivative of f is s multiplied by the Laplace transform of f minus f of 0. What that means is the Laplace transform eats derivatives. We're going to start with a differential equation. We're going to use the Laplace transform to eat the derivatives, and we're going to end up with an easier equation. But that's getting ahead of ourselves. We also have a formula for the second derivative of a function. The Laplace transform of f double prime is s squared. Laplace transform of f minus s of f 0 minus f prime of 0. Or the Laplace transform of the third derivative of f. Or the Laplace transform of the nth derivative of f. Now, you will note that there's a pattern here. You need to remember this. For the third derivative, we start with s cubed, and then it goes s squared, s, and then s to the power 0, or 1. Likewise, if we took the Laplace transform of the fourth derivative, we will start with s4, then s3, then s2, etc. I want to prove these formulae, and we can prove them using integration by parts again. The Laplace transform of f prime, by definition, is the integral from 0 to infinity, e to the power minus st f prime t. And again, I'm being lazy by not writing the limits here. When I write integral from 0 to infinity, really I mean the limit as capital R tends to infinity, etc., etc. Using integration by parts, we can move the derivative from the f onto the exponential function. And then evaluate this to get 0 minus f of 0 minus the integral from 0 to infinity of minus s e to the minus st f of t dt. Or minus f of 0 plus s multiplied by the integral from 0 to infinity e to the minus st f of t dt. But this red integral, we know what this is. This red integral is just the Laplace transform of small f. So we can prove the first formula. For the second formula, the Laplace transform of f double prime, we could just use part 1 twice. Let's suppose we take the formula in part 1 and we replace every f by f prime. So on the right side we have f prime here, we have f prime just here. On the left side we have f prime prime, or f double prime. Just exactly using the first formula but replacing f by f prime. Then we use the formula from part 1 again. We know what the Laplace transform of f prime is. This is just s, Laplace transform of f minus f0. And we obtain the formula that we wanted. I'm going to leave part 3 and part 4 for you to prove. For example, solve this initial value problem. Y double prime minus y prime minus 2y is equal to 0. Y of 0 is equal to 1. Y prime of 0 is equal to 0. I'm going to solve this in 2 different ways. Because this is a simple problem, we could use the method from chapter 3. This should be revision. The characteristic equation is r squared minus r minus 2. It has roots minus 1 and 2. So the general solution of the differential equation is c1 e to the power minus t plus c2 e to the power 2t. Using the initial conditions, we can find that c1 is 2 over 3 and c2 is 1 over 3. Therefore, the solution to this initial value problem is 2 over 3 e to the minus t plus 1 over 3 e to the power 2t. Now let's solve the problem again, but using the Laplace transform. The idea is, let's suppose we want to solve a difficult differential equation. In this example, we don't have a difficult differential equation, we have an easy differential equation. But let's just suppose that we're developing this method which we'll use for more difficult equations. Let's suppose we want to solve this problem, but it's very difficult to solve it. What we do is we're going to use the Laplace transform to change our difficult differential equation into an easy equation. We're going to solve the easy equation, and then we're going to use the inverse Laplace transform to find small y of t. That's the idea. So what we do is we start with the differential equation and we put the Laplace transform on both sides. The Laplace transform is 0. We can think of this as two different ways. You can either think of it, remember that the Laplace transform is a linear operator, and the linear operator always maps 0 to 0. Or you can go back to the definition of the Laplace transform. That's the integral of e to the power minus ft multiplied by ft. Put 0 in, you're integrating 0, which is 0. And because the Laplace transform is a linear operator, on the left side we have the Laplace transform of y double prime minus the Laplace transform of y prime minus 2 times the Laplace transform of y. We have our formulae, which I've written at the top. The Laplace transform of y double prime is s squared, capital Y, minus sy of 0, minus y prime of 0. The Laplace transform of y prime is s of capital Y minus y0. And then we have minus 2 multiplied by capital Y equal to 0. Then I want to put in the initial conditions. Remember, y0 was 1, y prime of 0 was 0, and again, y of 0 was 1. So I get s squared capital Y minus s minus 0, minus s capital Y minus 1, minus 2 capital Y is equal to 0. Or simplify this as s squared minus s minus 2 capital Y plus 1 minus s is equal to 0. We can rearrange this to capital Y is s minus 1 divided by s minus 2, s plus 1. Now we know capital Y, we can take the inverse Laplace transform to find small y. Before we can use the inverse Laplace transform, we need to use partial fractions, and I'm going to leave this for you to check. Check that capital Y is 1/3, 1 over s minus 2 plus 2/3 1 over s plus 1. And then let me remind you that the Laplace transform of e to the 2t is 1 over s minus 2. And the Laplace transform of e to the power minus t is 1 over s plus 1. So small y, which is the inverse Laplace transform of capital Y, is 1/3 multiplied by the inverse Laplace transform of 1 over s minus 2 plus 2/3 of the inverse Laplace transform of 1 over s plus 1, or 1/3 e to the power 2t plus 2/3 e to the power minus t, which is exactly the same solution we found using the previous method. Let's do another one. Again, this is a straightforward problem. If we wanted to, we could use the method from chapter 3 to solve this. But I want to solve this using the Laplace transform. What we do is we start with the differential equation. Y double prime plus y is equal to sine 2t. And we put the Laplace transform on everything. The Laplace transform of sine 2t, we know this. We can look this up in our table. This is 2 divided by s squared plus 4. The Laplace transform of small y is capital Y. And the Laplace transform of y double prime is s squared capital Y minus sy of 0 minus y prime of 0, using the formula from the theorem. Then we use the initial conditions. Y of 0 is 2, y prime of 0 is 1. We're going to get a 2 here and a 1 here. We get s squared capital Y minus 2s minus 1 plus capital Y is equal to 2 over s squared plus 4. We can rearrange the left-hand side to s squared plus 1 capital Y. And on the right side, I've moved 2s plus 1 over. Then to find y, we can divide both sides by s squared plus 1. Capital Y is 2s plus 1 divided by s squared plus 1 plus 2 over s squared plus 1, s squared plus 4. Then we need to use partial fractions. And we're going to be using partial fractions on this second term. I want something over s squared plus 1 plus something over s squared plus 4. Because s squared plus 1 is a second degree polynomial, on the top there must be a first degree polynomial. And again, because s squared plus 4 is a second degree polynomial, on the top I must go down, decrease by 1, decrease 2 by 1 to get 1 first degree polynomial. I'm going to leave it for you to check that this must be 2/3 and minus 2/3. In other words, A must be 0, C must be 0, B must be 2/3, and D must be minus 2/3. Now, the plus 1 and the plus 2/3, I want to combine to be 5/3. And then I want to arrange this so that it looks like functions which we find on the table of Laplace transforms. S over s squared plus 1 we find on the table of Laplace transforms. So we take the 2 out. Likewise, in the second term, we take the 5 over 3 out, and we leave 1 divided by s squared plus 1. For the third term, look, I'm not taking 2/3 out, I'm only taking 1/3 out. The reason is that 1 divided by s squared plus 4 does not appear on the table of elementary Laplace transforms, but 2 divided by s squared plus 4 does appear on this table. So I need to leave the 2 inside the bracket and then take just the 1/3 outside. And if you look on your table of elementary Laplace transforms, you will note that s over s squared plus 1 is just the Laplace transform of cos. 1 over s squared plus 1 is the Laplace transform of sine. And 2 over s squared plus 4 is the Laplace transform of sine of 2t. As soon as we know this, we can write down small y. Small y is the inverse Laplace transform of capital Y. So small y must be 2 cos t plus 5 over 3 sine t minus 1/3 sine 2t. Next example. Solve 4 derivatives of y minus y is equal to 0 with these initial conditions, 0, 1, 0, 0. We use the Laplace transform. We take the differential equation and we take the Laplace transform of everything. The Laplace transform of 0 is, of course, 0 is equal to the Laplace transform of the 4th derivative of y minus the Laplace transform of y. From the theorem, or from the formulae on the table of elementary Laplace transforms, we know that the Laplace transform of the 4th derivative of y must be S4. 4 here, so we start with 4. S4 capital Y, and then minus the initial condition. So minus S cubed, Y 0, minus S squared, Y prime, minus S Y double prime, minus Y triple prime. Y prime is 1, and the other ones are 0. So we get S squared, S to the power 4 capital Y, minus S squared, minus capital Y. Or we could write this as S to the power 4 minus 1 capital Y, minus S squared. This is our easy equation for capital Y. We can solve this just by rearranging to find that capital Y is S squared divided by S to the power 4 minus 1. Again, we're going to need to use partial fractions. On the bottom, there's S squared minus 1 multiplied by S squared plus 1. And using partial fractions, and I'm leaving this for you to check, this is a half over S squared minus 1 plus a half over S squared plus 1. Now, a half divided by S squared minus 1 does not appear on the table of elementary Laplace transforms, but 1 divided by S squared plus 1 does appear. So we take the half outside, and we're looking for the inverse Laplace transform of 1 over S squared minus 1. Likewise, we take the half out and we look for the inverse Laplace transform 1 divided by s squared plus 1. And you will be able to see from your table that this is a half sine t plus a half sine t. And if you're interested, the graph of this function looks like this. And that is the end of this week's topics. Next week, we're going to have our midterm exam, which will cover everything from the lessons up to this point. So that's all of chapter 1, 2, and 3, and the sections that we've talked about today, sections 4.1 and 4.2. Before I finish, I was asked on the discussion board to do one more example for a first order homogeneous equation. And the example I've chosen is one of the exercises in the lecture notes, actually exercise 2.8 part A, which said solve x squared plus 3xy plus y squared dx minus x squared dy is equal to 0. To solve a homogeneous equation, we need two formulae. We're going to use the substitution v is equal to y over x. And if we rearrange that equation and differentiate by the product rule, that would give us dy dx is v plus x dv dx. So what I'm going to do is I'm going to start with the equation, and I'm going to rearrange. First of all, rearrange to x squared plus 3xy plus y squared dx is equal to x squared dy. Divide both sides by dx, and then I'm going to divide both sides by x squared. We get 1 plus 3 y divided by x plus y divided by x squared is equal to dy dx. Let me just put dy dx on the left. This is the same as dy dx is 1 plus 3 y over x plus y over x squared. Now, you note that the right-hand side is a function of y divided by x. Therefore, this equation is a homogeneous equation. And when it's a homogeneous equation, we use the substitution v is equal to y over x. So instead of y over x here, we can write v, and instead of y over x here, we can write v. There we are. dy dx is 1 plus 3v plus v squared. We also want to use this green formula. dy dx is v plus x dv dx. I want to take the green formula and I want to use it to replace the dy dx. I have v plus x dv dx is 1 plus 3v plus v squared. We can cancel the v on the left with one of the v's on the right. To get x dv dx is 1 plus 2v plus v squared. This is a separable equation, and you know how to solve separable equations. What we do is we rearrange the equation so that all of the v terms are on the left and all of the x terms are on the right. There we are. dv divided by 1 over 1 plus 2v plus v squared is equal to dx divided by x. Because all the v terms on the left and all of the x terms on the right, it's okay to integrate this equation. We factor the left side. Integral of dv divided by v plus 1 squared is equal to integral of dx divided by x. And when we calculate these integrals, we get minus 1 over v plus 1 plus some constant c is equal to the natural logarithm of the absolute value of x. It doesn't matter where we put the plus c, we could put it on the left or we could put it on the right, it doesn't matter. I'm choosing to put it on the left, just so that I get the answer which was written in the lecture notes. Now that we have an equation for v, we want to substitute back in. I want to use this orange formula again. Instead of v, I want to write y divided by x. There we go. Minus 1 divided by y over x plus 1 plus c is the natural logarithm of x, which we can multiply by x to get x divided by x plus y plus the natural logarithm of the absolute value of x is equal to c. And this is how we solve homogeneous equations. So let me repeat this method. Start with the equation that you're given and rearrange it so that it's dy dx is equal to some function of y divided by x. As soon as you have an equation of this form, we can substitute in v is equal to y over x, and we can substitute in dy dx is equal to v plus x dv dx. Then we have a separable differential equation for v. Solve this equation as a separable equation. There we go. This is the solution of this separable equation. And then substitute in again, replace v by y over x, and then rearrange to get the solution. And that is the end of today's lesson. Do you have any questions? Now, it's not going to be multiple choice. You're going to have to write your answer and show all of your working and then upload your answer. If you look in the announcement section, I wrote a lot of information about the exam. You will be writing on paper and then taking a photograph of your answer. There should be enough time for you to solve the problems, write a good explanation, and then upload the photo.